Okay, so de Broglie matter waves were discovered when we saw that electrons diffract when you pass them through atoms, because the spacing of an atom, the electron, or a spacing in a crystal of atoms, I shouldn't say pass them through an atom, but you pass them through a crystal, the spacing of the atoms in a crystalline structure act like a double slit for the electrons, because the spacing of the atoms is on the order of the wavelength of the electrons' de Broglie waves, and we saw diffraction patterns. We saw that neutrons diffract. We see lots of subatomic particles diffracting as you pass them through a crystalline structure, because all those little spaces in that nice orderly crystal matrix act like double slits. So the other thing that we saw is you can relate these ideas of the orbitals, which you learn about in chemistry class, these subshells, to the standing waveforms that we learned about way back in the beginning at Unit 1. The different orbital structures are like the standing wave patterns that we saw for the open tube or the string fixed at both ends. So again, we only see this effect at the size of the atom, or at the atomic level distances or sizes. So things like electrons, protons, neutrons, things like that, we really only have to worry about the de Broglie wavelength for those types of things. Okay, so one of the first experiments that discovered this was something called the Davis-Germer experiment. The Davis-Germer experiment happened when these two gentlemen were trying to scatter electrons off of a nickel target. Now, nickel normally is what we call an amorphous solid. It doesn't have a regular matrix structure as a solid. But what happened is their vacuum tube cracked and they got a layer of oxidation on their nickel target. So they thought, well, we'll put it in the oven and we'll burn it off. Kind of like when you have to burn rust off your cast iron pan, you get it in a really hot oven and it burns the rust off. So they thought, well, we'll do this with our nickel target. What they did not realize is they had inadvertently crystallized their nickel. And so when they started passing the electrons through it again, instead of seeing a scattering pattern, they saw something a lot like the double slit. And they began to realize that these electrons were now acting like they were waves passing through a Young's double slit experiment. The reason this had not been noted before is because the electrons need to pass through very small openings. They need to be on the order of the size of their wavelength, just like we talked about with a double slit in Unit 6. Now, Erwin Schrödinger said, okay, so if these things are waves, they have to have a wave function. Remember, way back in Unit 1, when we came up with this idea of a wave function that told us about position and velocity and acceleration and all that. So he said, okay, gotta have that. But it's also got to obey conservation of energy. And there was no classical basis for what he wrote down. It was something that it was totally new and totally out of the box thinking for Erwin Schrödinger. But the idea was he gave it a form that was the wave function of the de Broglie wavelengths. The de Broglie wavelengths then could be described using their kinetic energy and their potential energy. Except in the quantum world, you can violate energy conservation, or it looks like you violate energy conservation, because you can have places where that position function puts you outside the classical region and you violate energy conservation when you have things like tunneling happen. You don't really, but it looks like it. Okay, so he wrote down this concept where you took the energy and you put it on this wave function, psi, which is just like the wave function we had in Unit 1. And you said, okay, the total energy still has to equal the kinetic plus the potential. But now these are differential equations and there's boundary conditions and all, it gets much more complicated, but it still works just like the wave function that we saw in Unit 1. Okay, so for your particular object, you have to describe a unique wave function and you have to make sure it satisfies the Schrödinger equation or it's not a description of that system. And these things get really complex really fast. So Schrödinger says the wave function tells us about where the oscillator is, sort of. Really what it does is it tells us its probability in being in that location. You have to take the probability by taking your wave function and you square it. And what that does is that doesn't matter if it's in a negative location or a positive location. It just tells you how likely it is to be in that location. And so really what the Schrodinger equation does is it tells you what is the likely position of the particle. So this is where we transfer from that strict solar system Bohr model of the atom to the electron cloud model that we see now in chemistry. So you can't know the position precisely. You can only know where it's most likely to be. So again, tunneling says you can have a particle outside the classically forbidden region. So radioactive decay is an example of tunneling, where this picture shows you that sometimes the alpha particle shows up outside the nucleus and it gets ejected from the nucleus very violently. So radioactive decay is not something literally just having little chunks break off of it. It's these very energetic emissions from deep inside the nucleus that are pushed away from the nucleus when they appear outside there. And that's why they're so energetic. Okay, and that's why they can damage tissue or kill cancer cells. All right. So Heisenberg's uncertainty principle tells you how to measure these things. So when you're talking about quantum systems, the thing you use to measure is light, because you can't stick a ruler in there, they're too small. Problem is, now we know that light and matter interact, so when you measure a system, you change it, you affect it. So Heisenberg says, okay, the more precisely you're going to measure this one thing, the more you're going to mess up this other thing. So the two things I want to measure are position and momentum, really velocity, but momentum. So if I really try to measure its position, I keep bombarding it with light, that light's interacting with it and changing its momentum. Conversely, if I want to measure its velocity, I have to keep bombarding it with light and I keep moving it. So I affect its position. So there is a limit to how accurately I can measure a quantum system, and that's determined by Heisenberg's uncertainty principle. So you cannot know exact values for either one of these things simultaneously. Okay, you have to sacrifice one to get the other. And this is usually on a scale of an order of magnitude because of light affecting our system. Now, the other thing that you know about from chemistry is Pauli exclusion principle, because that's where the quantum numbers come from. So what it does is it gives a uniqueness to each level of electron's energy level. So electrons don't like roommates. So what that means is no electron can share its energy state, its unique energy state, with another electron within an atom. Now, outside the atom, this doesn't make sense, because we're talking about the energy levels based on the nucleus and the atomic structure. So within an atom, electrons like to have a unique address. And so this is where you get your 4 quantum numbers: your principal quantum number N, your orbital or your subshell quantum number L, and this is where you get your electron configuration stuff like S, P, D, F, your magnetic quantum number M sub L, and your M sub S. And they all describe the location of that electron within the atom and give it a unique value of energy. Okay, so that's where we're going to stop with that, and we will come back and pick that up in a little bit.